Okay.
Yeah. How much are these worth?
4 points. 4 is the most you can get. So I'm going to hand out some. These will go along with our today's notes. The graphs they have aren't the best on the planet, but I think two things. One being it's being recorded, and two that I hope I do an effective job teaching. This is going to teach you a little bit about the geometry, and these would be good notes for you guys to go with. Those of you who are new to the class, I do have record all my lessons. I've actually started recording right now, and it goes onto YouTube. So find it, know it, and it's available to use as a tool. And I think, because the graphs are kind of cruddy, is it okay? Can everyone see? Yeah. And everybody see the board okay with the lights on? Everybody get one? All right. So, works perfect. All right, so this is chapter section 0, section 3, transformations in chord and plane. So our goal is to extend previous understanding of 4 transformations. And if you don't know what those are, I hope by the end of today we can help you out with it. So transformation is basically this: a picture that has moved, it has gone, or it's flipped over, or it's rotated, or it's increased in size or decreased in size. And then it can be a combination of all of those. And we're going to go over some of the theories in order to get through those, okay? So, okay, a transformation is an operation that moves or changes a geometric figure in some way to produce a new figure. Okay, you dealt with transformations with just your cell phone. You've taken a picture of your friend. You look at the picture. That picture you know is your friend. It looks like your friend, but it's a smaller version of your friend. Correct? So that's a transformation that, just has some sort of reduction, and there's some sort of scale factor of that reduction between the size of this photograph to the size of your actual friend. And we're not going to worry about that kind of thing right this very second, but that's where we're going to be aiming. But you've been dealing with this all along. If you go to a movie, especially if you go to an IMAX movie, obviously the people are so much bigger on the screen because, well, one, it's so cool to see stuff that big. And the more you have on a screen that's big, it's enjoyable to watch and participate in. Okay, so that's just one way of doing it. Another way of doing it is this desk. I could move it over this way, and we've not changed the desk. We've just shifted it. We could pick up the desk. We could shift it up. We could turn it upside down. It's just, we're not changing the desk. We're not changing the object. It's not like I'm taking a square and making it into a circle or a triangle into a star or anything like that. Okay? All right, number 3, I got to go along with my notes with this. All right, so you are going to, let's see. So using the vertices here on the right side of the front page, there's a small graph. And so what I want to do is I want to create that graph, and I'm going to draw what my original one is up here. So we have triangle of ABC. So you know that 2, 2 is right here. And then 5, 1 would be right here. And 4, 6 would be right here. So all I'm doing is I'm just taking the given information from here, and I plotted it there. That's long and the short of it. And I understand your box is going to be small to graph in, but the main thing is we're going to take A. And then as we do some sort of rotations or anything to it, we will then denote it as A prime or A double prime, a triple prime, quadruple prime, things like that. So 2, 2, 5, 1, 4, 6, we just put our ordered pairs and we've graphed that. Do we feel okay so far? So that's my original. So let's take blue. So then plot and label triangle A prime, B prime, C prime. Okay, so I'll go ahead and do this one in blue. You're like, why don't you do it in red like it does? It probably would have been the best idea in the world to do that way, but I didn't. I apologize. So -5, 1, 2, 3, 4 is our A value, and -2, 3, and -3, 8. 2, 3, 4, 5, 6, 7, 8. So that's our A point and our B point and our C point. So A prime, B prime, C prime. I guess I should have labeled this one as A prime or A, B, and C. So do you feel comfortable? This is the same shape, it's just moved. And an easy way to kind of look at this type of scenario, and we'll get there eventually, is what did I do wrong? Yeah.
You switched A prime B.
Yeah, A prime, B prime, I switched them accidentally. So let me just change that. Thank you. And so that should be -5, 4. That's A prime there, and that's B prime there. Okay, now it's very much the same shape. It's just moved over. You could describe this as it looks like it has shifted to the left and shifted up. Would that language be okay? So how much did we shift to the left and how much did we shift up? That might be something we look at. So if you looked at your point A and went to point A prime, it looks like it went 1, 2, 3, 4, 5, 6, 7 left and 2 up. So I shifted left 7 and 2 up. And that would be the same for each point. So this point should shift 7 left and 2 up, and this should go 7 left and 2 up. And that means our shape would have been the same shape. Does that language seem like it makes sense? All right, and then we're going to do we'll do this in the actual purple color. So A prime, I'm at 5, -2, so 1, 2, 3, 4, 5, -2. And this time I'm going to label that. And then B prime is 8, 3, so 8 and then 1, 2, and 3. B double prime. And then C double prime is 7, 2, so 7 and up 2. And that's supposed to be our A double prime right there. Let's make that, erase that. So does this one appear that it has shifted to the right and shifted down? And we could count our points to go where to where. So if I started with A, I'd say I went 1, 2, 3 right, and then I went down 1, 2, 3, 4. So 3 right, down 4. And the shape hasn't changed size at all, so we've maintained the integrity of this. We've just moved this around by shifting it right, left, up, down is all we've done. Okay, and as that goes, talk about our transformation. Okay, and so the notes to this is in the middle of the page where it says, how would you describe the transformations of ABC to produce the other two triangles? Well, they're shifting in the right-left position and they're shifting in the up-down position. Each point A maps to another point A. Each point B maps to another point B. Is that yours? This map that we're looking at is a map that you're going to see a lot more often, and it's not just because you took a picture of your buddies or you become part of the selfie craze or any of that kind of stuff. This stuff is a lot, it goes into computer generation. Do you ever watch a movie or a television show where an object morphs into another object or a person morphs into something else? This is the kind of math that takes place with a computer program. I understand if you went this to this, you could move a person and it looks like that person morphs across the screen. Or you could start changing. You could say, well, this point right here, that's going to go to this point over here and this point here. And every point could change a little with some sort of math function. And it could change into, whatever object you're trying to do. And a movie, and this dates me a little bit, that you would probably have seen is one of those Terminator movies where the one guy was like liquid and you could change into things. They were using this type of math at a little more complex level, but for the most part, this is where you could see it. So, moving down here, how would you describe the transformations? Well, we just did. We're shifting right and left, we're shifting up and down. Okay, some sort of combination. Is it incorrect if you say, well, can I go up or down and then right or left? It's going to do the same thing. It's just make it clear what you're doing. Don't be like shift 5 and 2. Well, is it going up, down 5, right, left 2? What's it doing? So be clear on how you're going to describe it, and we will try and be clear on that as well for you. May I move on? Okay, so we're going to start again. This would go with the next graph. We have triangle ABC. So let's go ahead and plot it. I'll try and stay consistent to my... And if you're having trouble graphing, that's what the original one will look like. I'm just going to do the last two, so then we'll just talk about this in a moment. Two. So, can everyone see the different colors up there? So the black triangle is our original one, ABC. Our red triangle is A prime, B prime, C prime. Someone think about some verbiage you could use about that. And I didn't mislabel this. Yes, sir.
It's reflected over the where the red one is reflected over the y-axis.
Okay. So pause there for a second. I like what you're saying. So we are reflecting the black one over the y-axis, which is the vertical component. And I like the reflection term. It's an actually perfect term to use. So is the point A and the point A prime the same distance from the y-axis? And is the point B and the point B prime the same distance from the y-axis? And the point C and C prime the same distance from the y-axis? Does everyone feel okay that when we call it a reflection, it's like a mirror? The y-axis is acting as a mirror, so you're reflecting. So whatever's closest to the mirror on one should be closest to the mirror on the other. So absolutely. With this y-axis, we're just doing this. And you had one more to say, Johnny. Okay, the purple one is then reflected over the x-axis. So it's satisfying the same condition. A to A double prime is the same distance from the x-axis. B to B double prime, same thing as C to C double prime, same distance. So this is acting as a mirror. What do you got?
But if you're going from C prime, from A prime, B prime, and C prime to the double primes, wouldn't it be a reflection and then a translation?
Oh. Oh. A reflection. So, okay, I like what you're saying. So I think you took a step. Right? Which way are you reflecting the red? Or are you doing a reflection and then translation?
You're reflecting the red over the x-axis.
So this would come down. So we're not seeing a triangle yet, right? So you're doing this?
Yeah, and then
Okay.
you're translating
The one that we can't see here.
Mhm.
Okay.
Over to the points.
I like that too. That does work. So, so once you see a prime, that means it's some sort of math is taking place. When you see the ABCs without the primes, that means it's your original. And normally you're going to talk about the translation with respect to the original. If you did say I could go from ABC to A double prime, B double prime, C double prime by reflecting over the y-axis, reflecting over the x-axis, then reflecting back over the y-axis. Absolutely right. That's another way to get there. Or you could say it reflected over the x-axis. So there's a number of ways that you could look at this. And which way is your brain going to twist it? I don't know. Is your brain going to twist it incorrectly? Maybe. But it's healthy to think about, is there a different way to go about it? So I think the next slide talks about, yeah.
I think it's actually a reflection over the x, then the y, not a translation. Because if you reflect the red.
So that's a reflection. Okay.
If you reflect the red over the x-axis,
okay,
you've still got A on the right, but in the other quadrant, you've got the A on the left.
Let's see. I'm gonna play with this a second. I understand completely what you're saying. I'm gonna see if I can I make this work? It's not gonna let me. So you're talking about there's a triangle down here that we're not seeing yet, but you're seeing the reflection happen twice.
Yeah.
You're right. Or you could just say from here to here is a reflection over the y, and from here to here is a reflection over the x. Or this one could go reflecting over the y, then reflecting over the x, and then reflecting over the y again. Am I on what you're saying?
Yeah.
I like it. And there's more ways. So some of you go, wait a minute. I was good until you just said that. Now there's a triangle that you're talking about that doesn't exist. But there's multiple ways to think about it. And how is your brain wired to think about it? I don't know yet. But we'll have some fun figuring it out. Okay? Can I pause? Is there any questions about what we've done so far? So again, the A, B, and C will normally be your original, the A prime and the B prime, or ABC primes and the ABC double primes, just mean that we're talking about different translations. So there's a whole bunch of different paths to take place, and it's healthy to think about, and it's a good portion of the class. Let's see here. Come down. How would you describe those? We just did we not? So one way we reflected over the y-axis, and then one way we reflected over the x-axis, or we reflected over the y, then over the x, and over the y again. So, please stop. My brain's shouldn't be going that way. But I promise it won't break. Do we feel okay? May I move to the next slide? Okay, so reflections can also use a line of reflection that is not one of the axes. So we can also have something that we reflect over that doesn't have to be the x or the y axis. Okay? So if I were to go from A as our original to B, what vertical line might we go over? Yes, sir.
1.
1? Do I have a second on that one? Yes, sir.
Well, I just want to know how would you rank it?
So we could say, I think you're absolutely right. So, does anyone know what this? Let's get fancy here. Go that way, and we're going to do this. This is being reflected over that. That's the line. Is that okay to say that? Okay, and I might not need to keep that there, so we'll just undo it. Because I don't want to confuse it too much. So the line right here, a linear equation that is vertical is what? Yes, ma'am?
Y equals 1.
Okay, hang on. Let's see. Let's make sure. So y equals 1 actually goes like that.
Oh, x equals 1.
X equals 1. So this right here, it reflects over the equation x is equal to 1. And let's just review a vertical line real quick. Okay, vertical line, that was the goofy one. If I gave you 2 points in algebra 1 and said, hey, find us the slope, what became 0 with a vertical line? The numerator being the top or the denominator being the bottom? The bottom. The denominator is a 0. That means it's a vertical line. So this particular line, this vertical line that we're talking about, vertical lines have an undefined slope. That's important to know. They make it awkward when we're finding the slope because you want everything y equals. And of course, when you're using your calculator, you're going, where's x equals? How can I draw that? A lot of times your calculator won't draw an undefined slope line unless you're in one of the other modes. Okay? So I like the fact this does appear that it's 2 from there and 2 from there. It reflects over it. Okay. What about from A to C? Yes, ma'am. It reflects over y equals 3. So it reflects over this line right here. And that line is y equals 3. Let's make sure we can. Oh yeah, that's over y. That's a y equals 3. What do we know about horizontal lines as far as slopes go? They're 0. Good. So vertical lines have an undefined slope because you're dividing by 0. Horizontal lines have a slope of 0, so the numerator would have been 0. Okay? So we can reflect over lines as well as other things. Is this okay? I don't know where I'm at my notes. I'm just keep going. Can I move on? All right, slide number 8. How many slides do we have? I think we have 700. We're here for a while. Clear your schedules. All right, start with ABC. So go ahead and plot ABC, 2, 2, 5, 1, and 4, 6. If you forgot what that looks like, it's drawn on the board. think it's the same triangle all the way through. Think. What do y'all think? I don't know, dude. Rotations? So hang on, if we were to rotate this, boom, and then if I were to take this and go, boom, and it makes that noise, and I go, boom, does that rotate back onto itself? What does it appear that we are rotating around? Yes, sir? 0, 0. 0, 0, which is also called the what? Origin. Now, we might be able to determine how many degrees we rotate, but this definitely has rotation about the origin. For those of you like, what's the origin again? Right there. So we have some sort of rotation. And the nice thing is, you know, we are 2 right, 2 up, 2 right, 2 down, 2 left, 2 down, and 2 left, 2 up. So we are maintaining the equivalent distance. We just have to be rotating around it. Woohoo! Who's making noise on me? Yes.
If you like plotted every point, like every decimal of a degree, would it make a circle? Like around going. Do you know what I mean?
So are we talking about the A points go from there, or are you
Yeah.
talking about every point?
Like whatever point.
So if we were to do this, this would create a radius of 2 root 2. And if you don't know how to get that, we'll get there eventually. So this would create the same exact equidistance. And yeah, I would definitely say there's a circle about that. So A's, if you kept going around, if you're doing degree amounts, not just saying 90, if you said 1 degree, 2 degree, 3 degree, 4 degree, I think that would very much take so. I like it. I lost what page I'm on my notes, and I'm sorry. Let's get to that one. Oh, there we go. Okay. So, let's see. So if I went from here to here, how many degrees would you think that rotation might be? Yeah, 90 degrees. Now, this is gonna. Okay, we have to look at a clock. You're absolutely right. How much? Counterclockwise. Clockwise. So a clock goes this way. So we say it rotated 90 degrees. And then how many degrees would it have rotated to here, would y'all feel? 180, and then, or actually this should actually come up to there. And then how many, come on. Going to there. How many? 270. Okay, so we have definitely rotations. Now, you absolutely could say this would rotate 90 degrees counterclockwise. Or this would, A to C, would be 180 degrees counterclockwise. And then A to C, that's 270. And you're like, there's way too much up there. But it's okay to use the reference of clockwise, meaning that's the direction the clock goes, or counterclockwise, as long as your degrees are the same. So negative 90 degrees clockwise, 90 degrees clockwise are 2 different locations, but definitely you could say that. All right, there's some things that I gotta, oh, wait a minute. All right, hang on, I think we can use, let's pick a different color. And let's do that color. Yes, you guys are like, it's too bright. I understand. That's a nice purplish. Kind of. Okay. Notice what's taking place here. From here to here was a 90-degree rotation clockwise. Can we say that? So what changed as far as our numeric values went? Which value changed? X or Y? The Y. What happened to the Y? Came negative. So let's look at this one. wait a minute. No, so it will look like the y changed here, but what about here? One's positive, one's negative. It looks like the y is negative, but something happened. Maybe they flip-flopped? Okay, so if the x and the y flip-flop doing a 90-degree clockwise rotation, hang on, would that work if I said that? If the x and y flip-flopped, and then if the y component changes value, that would mean this should be 6, -4. So if they flip-flop, they did flip-flop, and the y component became the opposite value. Oh, wait. So a 90-degree clockwise rotation. And I'm going to put a little note here because I'm going to forget. 90 degrees clockwise. If I went from x comma y, what would a rule be that you could say? And we're just making a judgment call. I don't have any proof that this is going to work other than, so we might have said the x and the y change places, and then what happened? Yeah.
The
X on the second part became negative. I mean, that's just what I'm seeing right now. Can I? And I'm just trying to make a rule to see if maybe that might work, but I don't know. Let's see. Let's go from here to here. It appears the x and the y's change signs 2, 2, 2, 2, but we also know it could flip-flop. We'll check here. So 5, 1. Oh, I have -5, 1. So the signs just changed. And then this one should be 4, 6. So the signs just changed. So hang on. We can make a little rule here again. We could say xy with 180-degree clockwise would be what? I got you. What do we got? What's the rule that appears to be? Yeah.
-x, -1.
Is that what you got back there? He's not listening. It's like talking to my wife. Okay. These are just some thoughts I might be able to say might happen if we were to go with these directions. Okay? And then hang on. We have this one to this one, which we were talking about 270-degree clockwise. So the xy, well, that looks like maybe the x just changes. Let's see. 5, 1, 1, 5. Wait, 5, 1. They flip-flopped and the x changed. Could those flip-flop and the x? Yeah. Could those flip-flop x change? Oh. Okay. So last little rule we could say is xy with a 270-degree clockwise. If I could write, I'd be such a better person. What letters? Sir?
y, x, and y would be
I like it. Those are some rules that we could probably say we're safe, at least on this problem. If we were to do other problems, perhaps we could see that this could happen over and over and over again. And then once we realize we haven't come to a scenario that it's changed, we might be able to say this rule does indeed take effect, which it sounds good. And the nice thing is those rules are indeed true rules that you come with. So anytime you have a 90-degree rotation, the x and y's flip over, the new y value turns negative. If you go 180, x and y stay as is, you just change the signs on both. You go 270, no matter where your point is, as long as you're going around the origin, you flip-flop your letters, and then you change your new x component to an opposite value. Holy crow, are you kidding me? How did we describe this? We did it? Okay, so hang on, let's move down. Is everyone okay? Anyone take a breather? Anyone need to poke your neighbor in the eye or anything? By all means. Realize you might get arrested for assault and battery, but hey, poke your neighbor in the eye. It's still cool. All right, how would you describe the transformations? I think we did right here. I think we did. I think we mathematically did. What does my arrows signify? Stirrupisms. There's not any math foundation to how my arrows are drawn. 10. We need to include for the following for rotations. Well, first off, we need to figure out what the center is. What's our center of rotation we're going around? It doesn't have to be the origin, but we want to have the center. So that'd be number 1. We need to include the following for rotations. So number 1, you need to figure out what you're rotating around. What's your center you're rotating around? And then we have to figure out our angle of rotation. 90, 180, or 270 is all we're really talking about right now. Of course, there are numerous rotations we do, but those are the important ones for right now. And then the direction of the rotation. Is it going clockwise or is it going counterclockwise? So then below that, you have CW and then CCW, which is clockwise and counterclockwise. So a 90-degree clockwise rotation is the same as a 270-degree counterclockwise rotation. So if I went 90 degrees like this, that's the same as going 270. Okay? And if I did a 180-degree rotation clockwise, if I go 180 degrees, follow my arm, comes around to that, well, that's the same thing as doing this. Gets to the same spot. So 180 is going to be the exact same, whether it's clockwise or counterclockwise. And then 270 degrees clockwise is the same as 90 counterclockwise. Okay? Oh my gosh. How many more pages do I have? Oh, are you kidding me? Oh my gatos. Voila. All right. 11:47, plenty of time. Okay. Plot the points. Here we go. 2, 2. 8, 4, 4. 3, 4, -2. C. And then red. 4, 4. 8, 8. That's not A. 8, 8. And 8, -4. 8. Well, can you tell me something from the black to the red? Yeah.
It's a dilation of.
Dilation of something, of 2. I like it. It's dilation. It got bigger. Okay. Made a larger image. And let's plot the other one, the purplish one. Let's see. I'm going to flip the lights off. I know you can't see. Let's set your phones and get that really bright light that everyone loves when you turn on and shine in your face. I'm just kidding. You should be able to see that, okay? Let's see. A double prime is 1, 1. B double prime is 2, 2. And C double prime is 2, -1. So from the black to the purple, yeah,
Dilation.
it's a half size dilation, okay. Cool. So how would you describe the transformation from A to B? So dilation is a transformation that stretches or shrinks a figure proportionally to create a similar figure. Oh, wait a minute. Dilation makes larger or smaller the same object to where you can still identify the same object. So each line has to have the same exact proportion to it in order to say, hey, this is the same object. So it's you looking at the photograph of your friend, and then you see your friend in the same outfit you just took a picture of going, you're a lot smaller here, you're a lot bigger here, you're a lot bigger here, you're a lot smaller here. Okay? Now, there's things you can do, I know, on your phones or your iPods or iPads or whatever devices you take a picture, you can change the pictures so they look a little goofy. And then there's that one where you take one person's face and put it on some other person's. I've tried following some of the stuff, but boy, it's exhausting. I think you guys are set with stuff. Just imagine now when you guys are older, what types of things your phones will be able to do. Kind of creepy, but it's kind of cool too. So dilation is a transformation that stretches or shrinks a figure proportionally to create a similar figure. So a similar figure, for the most part, in order for one figure to be similar to the other, the angles themselves have to maintain size. Okay? Dilations include both a center of dilation and a scale factor. So you have a center of dilation and a scale factor. So what was our center of dilation on our first triangle? It was actually 0, 0. And so what we could actually do, let's bring up this line, let's make that. If we were really good at drawing, if I was really accurate with drawing and not moving all over the place, we can see that 0, 0 is our center of this and how it expands from that. Does that make sense? So 0, 0 is our center in this case. What were the scale factors? We nailed it. So from the black to the red is a scale factor of 2. So scale factor 2, scale factor on this one of half. And we're relating it back to the original triangle. Okay, we're summing up. We're finishing up. Ready? That's what I wanted to We did it. We've not talked about it. We talked about it. All right. Identify going from blue to red. Reflection over the x-axis. Reflection over the x. Yes? And of course, when you look at yours, you can't see the difference. You have a black figure and a black figure. So we're going from this to this, and they're reflected over the x-axis. What's this one doing? It's a rotation. Okay? So I would say this is taking place, which would be what? 90 degrees counterclockwise. Or 270 clockwise. Good. Ideas? I think what we could do here is we're going to draw ourselves a rectangle right there, and then that rectangle kind of takes place still here. So this is telling us that it's doing either this or this. So 180 clockwise or 180 counterclockwise, same thing. We done yet? What time we out of here? Don't lie, because I'll find out when to go.
57.
57. Holy cow! You guys feel okay? Orderly. All right. Oh, what did I do with my? I didn't bring my notebook. All right. So, who has their book with them? You got yours? Is this it right here? So, worksheet 0.3 will be marked off tomorrow. Okay? And my office hours, if you need me, I'm off first, I'm off third and fourth. These are over in that math office over there. 7th and 8th period, I'm in the Career Tech Ed building, which is north of Stutler Bowl. Holy cow, we covered a lot today.